quickly today than at least we did on Monday and Tuesday, or Tuesday and Wednesday. It is a privilege and a pleasure to introduce the third and final lecture in the 2022 Van Horn Lecture Series with Professor Susan Trolier-McKinstry as our honored speaker. One of the recognitions that Professor Trolier-McKinstry has received is she was elected to the National Academy of Engineering in 2019. And for those of you who are not familiar with that, it is considered to be one of the highest professional distinctions conferred on engineers. The organization has been in existence since 1964, and it recognizes outstanding personal contributions in one or both of the areas of research, practice for education of engineering, or in pioneering new and developing fields of technology, or major advancements in existing technology, or innovative approaches to engineering education. And in the course of its history, depending on which website you look up, they have inducted over 2,600 engineers since its beginning. Again, depending on which website you look at, 10 to 12% of those have been female engineers, including the first female NAE member just in 1965, 1 year after the organization was founded. But so already to be a woman recognized by the National Academy of Engineering puts a person in a pretty elite club. But then when you look at how many of those women National Academy members have been in material science and engineering, as of 2021, there were only 23. There were some more inducted in 2022. But overall, about 1% of all of the National Academy of Engineering members are women in material science and engineering. And we are very fortunate that our Van Horn speaker is counted among those. But I'd also like to point out that two previous female Van Horn speakers are also members of the National Academy. Angela Belcher, who was our Van Horn speaker in 2019 in the area of biomimetic material synthesis, and Teresa Pollock, a distinguished mechanical properties metallurgist, was our speaker in 2014. So
I think Belcher was 2009.
Angela Belcher was 2009.
Yeah.
Right. Did I say it wrong?
You said 1909.
Okay. Can't read my own handwriting. Another distinction that wasn't in the handouts. Oh, and by the way, if you have not gotten one of these descriptions of the abstracts and the speaker bio, they're up here, just wave your hand and I'll get a copy back to you. But our Van Horn speaker has also written a textbook with Robert Newnham, one of her mentors, one of her teachers, and one of the great pioneers in the fields of ferroelectric materials. And I know for a fact that Professor Newnham was an outstanding teacher, and that Professor Trolier-McKinstry has also been heavily and positively influenced by his teaching. But materials engineering, bonding, structure, and structured property relationships was just published in its first edition in 2017. And I can tell from the quality of the lectures we've heard so far and the quality of other things I've heard from Professor Newnham, it's probably an excellent engineering textbook. So in this third lecture, it's a culmination of the two lectures that have preceded it. In the first lecture, we heard about advanced fundamental understanding of ferroelectrics, and our speaker's research group has pioneered analytical techniques that were really just at their infancy in 1992 when you began your career. And you told us about some of these properties of domain walls and how they get pinned that when ferroelectrics were first being pioneered by people like Professor Needham and Professor Cross at Penn State, the things that your group has found out would have just seemed miraculous and just twinkles in their eyes at the time. But so you really have advanced on a fundamental basis our understanding of very important physical behavior of materials. And then in the second lecture, you introduced us to some of the applications and how we engineers can exploit the physics and knowledge and understanding to make microelectromechanical devices out of ferroelectrics. Today's lecture, we will now expand into the area of ferroelectric memory storage, but now extending into not just thin film applications, but into three-dimensional energy storage. And it's going to be put in the context of reducing the energy demand of electronics and data storage. I don't need to tell any of you how much our life is dependent on data banks, memory storage, and how the demand is only going to increase. And to the extent that we can reduce our energy consumption using new novel material architectures, materials engineering may make a very important contribution to sustainability. So with that, I introduce our speaker.
So let me start out by saying I have a terribly squeaky voice today, so I will do my best, but if I'm unintelligible, if you need me to take the mask off, just let me know. So I do have the pleasure to speak about some of the work that we're doing on new materials for ferroelectric microelectronics. This work is based on a center that I direct that includes partners from Penn State, Purdue University, University of Virginia, University of Pennsylvania, Rochester Institute of Technology, Oak Ridge and Sandia National Labs, Georgia Tech, Carnegie Mellon, and University of Tennessee. And the motivation behind the work is really shown here. Depending on who you read, estimates are that computation accounts for something like 5 to 15% of worldwide energy consumption. And that number is growing over time. So this just shows you a time series up through 2030. And the energy forecast that's associated with computation. Certainly, we know that data centers alone require enormous amounts of power due to the needs for cooling, among other things. And we also know that we're projecting that the Internet of Things is going to become more and more important. In the Internet of Things, for the most part, we don't have all the computation that we need locally, which means that all of that information, all that data needs to be transferred up to the cloud, and cloud processing needs to be done on it, and the results transmitted back. That is going to make this number balloon. And so it behooves us as material scientists to imagine, can we do anything about that? And this shows you kind of some of the motivation for the approach we've chosen to adopt. So the CPU is the central processing unit. And the different levels that I'm showing there in black are levels of memory. And the key points to recognize is that there are multiple levels of memory in all electronic systems. And the farther away I have to go from the CPU to get to the memory, the more energetically expensive it is. So you can see there's an order of magnitude difference in terms of just extracting information from memory if I go from level 1 to level 3 memory. And so that is in part a function of the architectures that we choose to use for processing. And von Neumann early on said an appropriate architecture would be to have the processor here, the memory physically distinct from the processor, and there's relatively few points of connection between them. And that introduces both this huge energy penalty. It also produces something like 80% of the system time latency. And so if you could move from a scenario where you have, here's the normalized density of memory logic interconnections. Right now that number is fairly small because memory and processors are physically distinct. That costs us lots of energy because we have to transfer data and the results back and forth. If we could move a scenario where instead of having that memory be distinct, it was integrated directly on top of the processor, now you should be able to make a step change in the memory logic interconnections. And if you could do that, you should be able to remove substantial fraction of the energy burden. Depending on whose numbers you read, it could be up to 1,000-fold reduction in the power associated with computation. That's not trivial. And it should substantially reduce latency. So let's imagine that this is, that sounds like a good thing. How would we go about doing that? Well, one of the key constraints is I can't do anything up here in putting the memory on that damages anything underlying it, which means I get to use temperatures of no more than 400 degrees C, and I need to use processes that are fully compatible with front end of the line silicon semiconductors, but now we're going to do this all on the back end of the line, which means a lot of the materials scientists' tricks that we use, epitaxy, no hope. I have to do this on polycrystalline tungsten plugs. I have no access or very limited access to temperature. So what really can we do here? And what I show here is a comparison of, so here's our central processing unit. Here are potential approaches to the various levels of memory. And here are some of the approaches to non-volatile memory that are being explored. So if it's non-volatile, I don't have to continually refresh it. I don't have to pay the energy burden of continuing to update the memory. So if we're going to put this memory on the processor, we'd like it to be non-volatile. And kind of what's shown in green on this table is good. What's shown in red is likely to be a showstopper. And you can see that for STT-RAM, phase change memory, resistive memory, NAND flash, ferroelectric field effect transistors, none of these technologies are perfect. But we got a fair amount of green here for the ferroelectric field effect transistor. Let's see whether we can use the property of ferroelectricity to provide this non-volatility. So recall that in a ferroelectric material, I have a spontaneous polarization, and I can reorient the direction of that spontaneous polarization with an applied electric field, such that I could use, say, a polarization state up as my 1, a polarization state down as my 0, and those states will remain for very long times. So has anyone ever done this? Well, work on ferroelectric memories started in the 1950s, and at the time we simply didn't have any of the required processing to make this viable in a semiconductor foundry. But subsequently, there's been a lot of work on it. There's a lot of potential advantages, nice short access times, excellent retention, good endurance, low power, functional circuit performance. And there are materials that are in commercial production by Texas Instruments, Cypress, Fujitsu, and Rome, mostly in ferroelectric random access memory stacks, where we have a ferroelectric material that sits above the front end of the line transistor. And now we got to think through some of the problems. The materials that they use for this application to date have been lead zirconate titanate and strontium bismuth tantalate, both of which crystallize at temperatures in excess of 550 degrees C, and both of which turn out to have pretty dismal scaling performance. So it turns out that below about 70 nanometers, they've been in thickness, they've been unable to continue to scale. So there are devices out there, they are commercially viable, but they're all really low density memory. This does not solve our fundamental problem. And so, are there other materials out there? And if we're going to go look for other materials out there, we need to really be able to look for something that we can stack, not a single layer of memory, but many, many layers in sequence. And this kind of shows why. This shows you the data for NAND flash. But about 2016, they could no longer continue to laterally scale and use lateral scaling as the way that they increase the memory. And now they stack in 3 dimensions. And so we're not going to compete with that if we go back to a 2-dimensional memory format. So the basic approach that we're taking is to say we need an entirely new class of materials. They need to be back end of the line compatible. I don't get epitaxy. I don't get much temperature to work with. And so how do you make new materials? It's very often through a combination of really brilliant theoreticians, excellent materials growth, and really advanced characterization. And so what we're trying to do is to invent new families of materials here and then demonstrate them in first-level devices. Alas, the Department of Energy decided they would not allow us to study architectures, which would actually have closed the loop. It would have been the right thing to do, but they said no. So we're basically demonstrating the first levels of devices of these new memory materials. And what we're trying to do is to explore the fundamental mechanisms that are associated with how do I make a material ferroelectric, how do I turn that on and off, how do I develop the processing science that I can make these materials at relevant temperatures, how do I demonstrate that they function in devices, and how do I characterize these materials at time and length scales that have been inaccessible previously. So what do I need out of this ferroelectric? What I need out of this ferroelectric is going to depend on what device instantiation I use. So if we are going to use a ferroelectric field effect transistor, where we're using the spontaneous polarization to control the carrier concentration on a semiconducting channel. So if I have a polarization up, it's positive at that surface. So I can, for example, drain carriers out of some channels. If I flip it the other direction, the carriers will accumulate in different ways. That's how a ferroelectric field effect transistor works. And for that application, for realistic semiconductor carrier concentrations, I need about 1 to 10 microcoulombs per centimeter square. Anything beyond that doesn't help me at all. In fact, it's problematic. In contrast, if I go for a ferroelectric random access memory, now I get the most signal margin if I have the biggest possible polarization. And honestly, below about 5 microcoulombs per centimeter square, I can't detect the difference between 1 and 0 anymore. So I'd really like to be well beyond 20 microcoulombs per centimeter square. Ferroelectric tunnel junctions, people are still kind of figuring out how that works. We actually change the propensity for tunneling through extraordinarily thin ferroelectrics based on the interaction between the polarization and the contact materials. There again, I'm going to need a giant polarization. And there are some proposed devices where we actually want to use this ferroelectric as a semiconductor itself. So it will matter. There's not one size fits all for this particular application, except I want it to be non-volatile. I want it to be low power. Industry won't care if it's not compatible with CMOS, so I don't get 50 volts. So how do I do this at 1 volt? And how do I do this enough times that I could actually preferentially do compute in memory? So how would you go about designing a material for a ferroelectric application? Well, there's a couple of possibilities. We have lots of materials which are polar, but which we don't know how to switch. So the polarization, we grow it in that orientation, but we don't necessarily know how to switch it. And if you can't switch it, it's not ferroelectric. So can we start with a material which is polar and engineer the switching barrier? Alternatively, can we start with a material that's not ferroelectric at all and start shoving atoms around in the solid to induce a polarization and switch it that way? For both of these, how do we actually grow the thing? It's likely to be very far from equilibrium. We will need, as we develop these new materials, to understand all the fundamentals of the kind that I talked about on Tuesday. How do these things switch? How do I control polarization, nucleation, how do I control the material science? And we speculate that there's actually going to be a performance tetrahedron that's going to say, I'm going to design the best materials based on how big's the polarization, how big is this elastic stiffness. The stiffer it is, the harder it is to reconfigure bonds in the solid. How big's the band gap? If I have to blow the material up to switch it, that's probably not going to be appealing. And yeah, I think we've got all of them there, and the coercive field. So I've talked you through some of the ways that one goes about engineering things. This was my advisor, Professor Newnham. He did hand-drawn view graphs of everything. When he retired, I got all his hand-drawn view graphs, and he laid out what he thought were the ways that you made material polar. And we speculate that there's another one. So we've added this, not in his beautiful handwriting, but we've added this one, which is that always, when you poise the material at the brink of a structural instability, the susceptibilities go up. I should be able to shove atoms around easier when there's a propensity for moving them. And so we speculate that if you take a phase diagram, poise the material near where there's going to be a structural phase transformation, we might be more likely to generate ferroelectricity. And this shows the materials that we're working on. Hafnium zirconium oxide was actually, first publication is in 2011, so this is a material we are not responsible for. But it is CMOS compatible, and it is being very widely explored by industry at the moment. Aluminum scandium nitride was demonstrated to be ferroelectric in 2019. This is the Wurtzite structure. In the Wurtzite crystal structure, I have tetrahedral coordination on the cations in question. So one neighbor up, three neighbors down at an angle like this. And in order to switch it, I have to take that atom, force it through the space between the three atoms below it, and invert the direction of the tetrahedron. So that's how this material switches. And so what kind of structural instability do I go look for? One that starts by flattening that tetrahedra. And if I start with a flattened tetrahedra, I don't have to move the atoms around as much. And that's really what the group at the University of Kiel demonstrated was possible. Alas, this material tends to get a little electrically leaky, and so it's hard to scale. And the thinner it goes, the worse, the more leaky it gets. It's hard. And so we've developed two analogs, aluminum boron nitride and zinc magnesium oxide, which undergo the same mechanism. We poise the material on the brink of a structural instability between the Wurtzite structure and the rock salt structure. And when we do that, these materials become honest-to-goodness card-carrying ferroelectrics. So very cool. We've also demonstrated that there's a bunch of materials that might have been ferroelectric that aren't, at least as far as we can tell. And that also turns out to be useful just to say, don't go here. So, where do we use aluminum nitride? It is ubiquitous in thin film bulk acoustic resonators. That is the filter system that's used in every cell phone. This is an industry fab friendly material. And so we need to be able to take that material and make it ferroelectric. And my colleague, Professor John Paul Maria, said, well, think about this from a crystal chemistry perspective. If I have to force that cation down between the three neighbors, well, let's start with something that likes to sit between those three neighbors anyway. So boron nitride, hexagonal boron nitride. You put the boron in 3 coordination with its nitrogen neighbors in that intermediate arrangement. So can we take aluminum nitride and put boron rather than scandium in? And the answer is yes. It turns into a very beautiful ferroelectric material. The spontaneous polarization is nearly independent of temperature, up to about 300 degrees C. You will also notice that the coercive field or the electric field required to switch from the up to the down polarization is on order 5 to 6 megavolts per centimeter. That's unhappy. Now I have to make it very, very thin to drive that at 1 volt. So there is a huge need here to figure out the mechanism to lower that energy barrier for polarization reorientation, but it's incredibly strongly temperature dependent. Okay, the temperature dependence is enormous. We dropped the coercive field factors of 2 within a couple hundred degrees. And so what we find is that you see that data plotted here. So here's the coercive field, here's the breakdown strength. As we get hotter, we actually get a little more room between where the material flips and where it blows up due to dielectric breakdown events. And that's really cool because we've taken aluminum nitride itself. I taught for 30 years that aluminum nitride is a polar, non-switchable material. And I was wrong. And isn't that fun? That you heat the material up, you change the energy barriers just enough, and even materials that we thought of as never being potential ferroelectrics become ferroelectric. That says that first model of starting with a polar material and engendering a ferroelectric instability, the ability to reverse it, is a viable way of making new ferroelectrics. So this shows the composition dependence of the coercive fields and the band gap. As we add boron, the band gaps stay nice and high. So we start about 6.2 electron volts, and we only drop to just about 5 at the limit of the boron solubility. The coercive fields don't vary as much as I was really hoping this would plummet, but it doesn't. Nature didn't give us that. And part of the reason it doesn't is that it turns out that the boron doesn't do what we projected. It doesn't flatten the tetrahedra very well. And as a result, we don't change the crystallographic C by A ratio very much at all as we add boron into it. It's a totally different mechanism from aluminum scandium nitride. That's fun. We're still trying to figure it out. But we can go through and do the baseline characterization. This shows the temperature dependence of the relative permittivity. These materials do not have phase transitions up to 300 degrees C. As far as we can tell, they do not have phase transitions below 1,000 degrees C. There are some first principles calculations that say maybe this material would become nonpolar above 3,000 degrees C. Well, that's cool. It's not a soft mode ferroelectric either. So totally new mechanism for making ferroelectric. There is no nonpolar state at elevated temperatures. Very cool. And so this shows data on aluminum boron, as aluminum scandium nitride, aluminum boron nitride, and aluminum nitride measured as a function of temperature. You can see that the hotter it is, the lower the coercive fields are, but the loops stay very, very beautifully shaped. And look at the magnitudes of the polarizations. 125 microcoulombs per centimeter square. That is polarization to burn. For an electrical engineer, that says, I can scale my material laterally because I don't have to, I will have enough electrons to measure switching very small, absolute sized capacitors. So let's plot the coercive field as a function of temperature, excuse me. And we find that it drops roughly linearly between room temperature and about 300 degrees C. If you do an Arrhenius-like plot and assess what the pseudo-activation energy for polarization reversal is, it's on order 20 to 30 millielectron volts. That tells you right away that these materials do not switch by an intrinsic mechanism where all of the tetrahedra flip from one orientation to the other orientation simultaneously. That would require vastly, vastly higher energies because I have to run a bond break for this process to occur. I'm going to come back to that point in a bit. The other thing that we see is that very often, the first time we try and switch one of these, it looks like a beautiful linear dielectric. And we actually have to switch it a couple times before the polarization starts to reorient. This material undergoes a process called wake-up. And wake-up's a known phenomenon in ferroelectric films. It happens for a variety of different reasons. In the hafnium zirconium oxide, it happens actually because you start shoving oxygen vacancies around when you field cycle these materials, and that changes the phase of the material. You actually go on a phase transformation from the non-ferroelectric tetragonal phase to the ferroelectric orthorhombic phase. In the perovskite and the perovskite layer structure materials, very often wake up is associated with changing the defect chemistry in the material. So you can pin a polarization on any local electric or local elastic field. So if you get the point defect concentration wrong initially, you can stabilize one polarization state over another. And we are pretty sure that's not how these materials wake up. We have a totally new mechanism for wake up in these materials. We can justify that based on the fact that there is a very strong polarity dependence to the etching on all the Wurtzite structured compounds. They etch faster when they're pulled in one direction than they do in another. So you can literally put it in an acid bath and say what the polarization state was. And so we hypothesized that polarization reversal requires a critical density of these oppositely oriented nuclei, and the materials grow completely pulled down. So the original polarization is all associated with the alumina nitride units in that orientation. So how would we prove this? We use the same sorts of basic fundamentals that I talked about on Tuesday. Recognize that I have intrinsic responses, I have extrinsic responses due to the motion of domain walls, and anytime I move a domain wall around, there will be a hysteretic component to it. Let's go find that at subswitching fields by doing Rayleigh analysis. And so we speculated that the way these materials would switch is the same, is via basically an inversion of the puckering of the puckered hexagonal ring in the Wurtzite crystal structure. The animation that you're seeing here is one that I took. This is a hypothesis. This is not proven. It actually turns out to be brutally hard to prove this. But we took real known anti-phase boundaries in gallium nitride, which have exactly defects of this type, and we speculate that if I can move that defect back and forth, I should be able to run polarization reversal. And so we do things like say, well, is there really like behavior in these materials? And the answer for the most part here is permittivity as a function of the amplitude of the electric field. And before I wake the material up, they are not really like behavior. They behave like there are no domain walls. Take the same material, run a polarization reversal process a couple times, and look what happens to the relative permittivity. It goes from about 12.5 to about 14. That's an enormous change in relative permittivity. I don't get to change intrinsic responses that much. It just doesn't happen. That happened because we built domain walls into the solid. And once we built domain walls into the solid by waking the material up, the basic permittivity went up, and the slope on the permittivity as a function of the amplitude of the AC electric field goes up. And we've been able to map that as a function of temperature and frequency. And we believe this is the real way that this family of materials wakes up. We grow them in a single polarity. So in our particular case, the aluminum boron nitrides all grow pulled down. So you start with a material with no domain walls in the pulled down state. You run the first hysteresis loop, and it behaves like a linear dielectric. So a very small change. The slope on that is simply the dielectric constant of the solid. When we field cycle it, we believe that we are adding nuclei of oppositely oriented polarization into the material. Once we have them there, they're hard to get rid of. And each of these nuclei can only sweep a finite volume in the time that we give it for polarization reversal, which means that I need more and more and more nuclei before I can get the entire hysteresis loop to wake up completely. So these materials are really different from conventional ferroelectrics. This is a plot of the remnant polarization as a function of the Curie temperature. Here's what we're working with, only we have to speculate that the Curie temperature is like way off this board, somewhere in the next room over there. They're very different. Enormous polarizations, incredibly, incredibly temperature stable. And if you look at aluminum boron nitride compared to its analog aluminum scandium nitride, you can see why we are interested in it. So this shows data for an aluminum scandium nitride. This is beautiful work out of the University of Pennsylvania, where they've scaled the thickness. And you see that hysteresis loop looks a little funny. If you look at the top of the hysteresis loop, when I decrease electric field, the apparent polarization goes up. Okay, that's bad physics. Polarizations, excuse me, will tend to align parallel to the electric field, not anti-parallel to the electric field. That is an artifact associated with leakage. And we cheat and hide that leakage as well as we can by making the measurements so fast some of the charge carriers can't keep up. So this thing looks like a football. If you measure it at low frequency, measure it fast enough and you say, all right, I'll squint at it, that looks ferroelectric. Here's data from the Tokyo Institute of Technology. Looks much nicer looking hysteresis loop, but they've gone even an order of magnitude higher in frequency to hide some of its defects. And that's because when you add scandium to aluminum nitride, the band gap comes down really fast. And so it's not that they've grown bad films, they've grown amazing quality films, but it's just really hard to keep the material insulating enough at 6 megavolts per centimeter to avoid leakage currents. Here is the aluminum boron nitride analog. You can see at 50 and 100 nanometers thickness, so comparable to these, much nicer shaped hysteresis loops, and we were able to measure it at much, much lower frequencies. We're hiding less. So this material, the band gap doesn't drop as fast, so it looks pretty appealing for this application. And so let's build it into a ferroelectric field effect transistor. And this is not a great material for a ferroelectric field and transistor. Its polarization's too big, but let's try it anyway. And so my colleague Tom Jackson grew one in. He did end up using top and bottom gates so that he can terminate the electric field. And these are, honest to God, ferroelectric memory elements. So they show all of the transistor characteristics that one would hope for. But the coercive fields are still brutally high. Okay, 6 megavolts per centimeter. Now I got to get really, really thin before I hit a 1 volt switch. So can we figure out another material? Well, we have the periodic table. Let's contemplate what else we could do on the periodic table. So aluminum nitride has the wurtzite crystal structure. All of you will recall that zincite has exactly the same crystal structure, and it's way more ionic. And because it's way more ionic, maybe it'll be a little easier to do this. So what could we throw in to zincite in order to poise the material on the brink of a structural transition? Well, I want to push it towards the rock salt structure to flatten that tetrahedra. Where on the periodic table do I have something like 6 coordination with oxygen? Magnesium. So we made a zinc magnesium oxide solid solution. The phase diagram is shown here. There's actually thermodynamic stability says I don't have much room to put much magnesium in, but there is an enormous literature on this that says in thin films you can get about 40% magnesium into this structure. And here, the band gap actually goes up when I add magnesium into zinc oxide, so very helpful. Use the same trick. We use reactive magnetron sputtering. Again, work from John Paul Maria's group. I'm showing here data grown on sapphire single crystals, but we've also grown this on polycrystalline, on silicon, on polycrystalline tungsten. And what you see is that you get beautiful orientation. The material is another card-carrying ferroelectric. Here, though, look at the magnitudes of the fields required for polarization reversal. Instead of being 4 to 6 megavolts per centimeter, it's under 4 megavolts per centimeter. So that's helpful in terms of getting to a 1 volt device. So we lose a little bit in terms of polarization. These materials are typically closer to 80 microcoulombs per centimeter square than 125 microcoulombs per centimeter square. And completely serendipitously, we were using second harmonic generation to look at the domain states in these materials. This is work of Professor Venkat Gopalan, and he does SHG polarimetry and found out that these materials have really, really big second harmonic generation coefficients. So this is basically the worldwide literature on SHG coefficients as a function of band gap. Can always make the material more responsive by making it absorb a little more. That increases the interaction between the electric field vector of the light and the electrons in the solid. But things aren't as transparent at that point. And so kind of the world standard material is lithium niobate, which I show here. You see the zinc magnesium oxide has a slightly bigger band gap than lithium niobate. It has twice the second harmonic generation coefficient, and I can put this on any Selper's rate I want to. We have grown this stuff on polymers with coefficients like this. So that's a game changer in terms of integrated optoelectronics. We totally weren't expecting that, but I think there's really going to be some fruit there. The zinc magnesium oxide, excuse me, as is the case for the aluminum boron nitride, has this hugely strong temperature dependence of the coercive field. Again, we get pseudo-activation energies on the order of 20 millielectron volts. That says it's switching by this domain wall flavored mechanism. We also get wake up in this material. The wake up here is actually a little easier to study because these materials have a bigger difference between kind of the coercive field and the maximum field the material will tolerate. So I can just jack the field up and study it at higher electric fields. And so we've demonstrated that you can actually do single cycle wake up in this. So one application of a large voltage and you run through the entire ferroelectric hysteresis loop. So that looks like a second really promising candidate. And let's just step back and say, will the semiconductor community care? Okay, and so the old rule of thumb, it's gotten better, but the old rule of thumb is a semiconductor foundry would introduce one new element every 10 years. Okay, fab engineers are conservative, and they're conservative for extraordinarily good reasons. You can't afford to take down a line because you've contaminated something. So are these materials even relevant? Well, aluminum boron nitride in particular looks sterling. We use aluminum as metallization already in these stacks. Boron is the p-type dopant, and nitrin is used in every gate stack. And we're doing some of this preparation at room temperature. It's all sub 400 degrees C. So we're growing the aluminum boron nitride from 200 degrees C down to room temperature. The zinc magnesium oxide, ballpark 100 degrees C down to room temperature. So we've solved the integration issue. We can do this material on tungsten plugs at relevant temperatures with relevant electrical properties. But there's some things that are a little scary. That is the hysteresis loop of lead zirconate titanate compared to the hysteresis loop of aluminum boron nitride. That is open, but the coercive field is like 50 kilovolts per centimeter. Recall that all the energy in this, or all of the area in that loop is energy loss, which means every time I run this polarization loop, I'm dumping energy into the solid. That is something we're going to have to engineer out. I suspect that we will need to learn how to create nuclei which are chemically induced that basically facilitate the reorientation process at lower absolute electric fields. So we have work to do on dissipated energy. So will this thing actually hold a polarization? So it's very useful when you set a memory state, if that memory state can be retained. So I could come back and read it later on. Otherwise, that my memory develops amnesia and I'm unhappy. So this is the standard retention characterization for ferroelectric random access memory. You measure in the same state. So you put the polarization in the up direction, you bake it there for a while. And when you do that, all the point defects and everything that's going to move tends to move to stabilize that state. And so when I come back and try and read that state, it tends to be really stable. Where most ferroelectric memories fail is when you write it into this state, bake it into this state, and then flip it into a down state. And it's going to try to go back to the one that you flipped it in, or that you baked it into. And so we just looked, how bad is this problem in the new Wurtzite materials? And compared here, the set of material at the bottom, that's lead zirconate titanate. That is the data from Texas Instruments on their commercial product. This is not our data. These two are our data. You see the aluminum boron nitride, zinc magnesium oxide, we got signal margin to burn, and they're incredibly stable in the same state. And they're incredibly stable in the opposite state. We have baked these for 1,000 hours at 200 degrees C. In the case of the zinc magnesium oxide, we actually can't find a loss in polarization, which means that when we extrapolate out for aluminum boron nitride, we start to see a little loss. But we've extrapolated out to a 10-year same 10-year opposite state measurement, and we still have 200 microcoulombs per centimeter square to read. That's huge. Lead zirconate titanate, they call that bit failed at 5 microcoulombs per centimeter square. So retention, we have solved that problem. These materials retain data brilliantly. What they don't do very well yet is to flip the polarization over and over and over again without blowing up. So they don't actually fatigue. They undergo dielectric breakdown events. And you can see what's happening here. So this is apparent polarization as a function of the number of times we rewrite it from poled up to poled down. With 100 nanometer platinum dots, you wake it up, that's good. The polarization is stable for a little while and it starts creeping up. That's not physical, that's all leakage. And then the apparent polarization starts to plummet. That's associated with the fact that we're actually, in this case, blowing up the perimeter of the sample, and we fail it into a open circuit condition so we can run the next cycle, but not what you really want to do. The problem is a little bit less severe with tungsten, and it's much less severe if you actually design in a field plate that lowers the field concentrations, and which is what I'm showing here. So here is a electric field simulation. This is an aluminum boron nitride, platinum top electrode, tungsten bottom electrode. And here are simulations of the electric field near the perimeter of the electrode edges. And not surprisingly, electrode discontinuities, you end up with huge field concentrations. So even though these materials have big breakdown strengths, if you apply electric fields that are many times the course of field at the electrode perimeter, you're very likely to blow the material up. And so what we're learning how to do is to design field plates. You'll notice the same material, same electric field. We can drop the maximum field if we're a little more clever about the design than the average material scientist. And we're starting to get rid of that problem where those black specks, we've literally blown the material up and removed the electrode. You'll notice all those failure events are around the electrode perimeter where the field concentrations are the worst. So we have lots of extra work to do here. We've nowhere begun to probe all of the things that we need to do. Among the things that are really critical is to improve the crystallography of that very first interface between the bottom electrode and the aluminum nitride. And so that's where we're poking at now. I've got just a few minutes, so I'm going to say a tiny bit on hafnium zirconium oxide, which is the other alternative. And hafnium zirconium oxide, you can see why people already care about it in this plot. So this shows physical gate length as a function of publication year. Here's why people quit trying to scale the perovskites. They literally could not get them to go any smaller. They stopped scaling. And so that's why they basically haven't gotten much past the 130 nanometer node. You can't do really high density that way. The hafnium zirconium oxide materials are scaling like the rest of the processor scales, so that you can actually make scaled devices. So people are very excited about this and are exploring it for a number of different applications. So it's very cool that it's scalable. It remains ferroelectric to 1 nanometer. Oh my goodness, that's pretty impressive. That's a scaled device. Lateral scaling is easy. Hafnia has been the gate material as an amorphous material for the last 10 years. Semiconductor industry is like, this is a material I'm very comfortable working with. You can grow the materials by atomic layer deposition, but nobody knew why it was honest to God ferroelectric. we should probably know this if we're going to engineer with this, particularly if we're going to try and figure out how do we beat the corrosive fields down by about a factor of 2 to improve the reliability. And so our colleague Andrew Rapp from the University of Pennsylvania has now published a paper where he lays out exactly why this material becomes ferroelectric. So you actually start here with one possible state. That's the cubic prototype fluorite structure. And the first thing that happens is that the material undergoes a tetragonal distortion, which is not ferroelectric. That gives you those 6 states, and it can tetragonally distort this way, or this way. So those are the 6 states, because I can go, up, down, forward, back, left, or right. Once I have that tetragonal state, we actually go to an antipolar state, which means on a unit cell level, some of it goes polarization up, next bit goes polarization down, so it's not ferroelectric. But once you get to that antipolar state, excuse me, under the appropriate levels of strain, you get all of the ferroelectric states coming out. And so that's what you're seeing out here is all of the possible orientations for that polarization. And it depends, tragically, on absolutely everything, including the point defect chemistry. So many of you will have taken Professor Zaroglu's electroceramics course. What do we use fluorite structured oxides for? Solid state ionics, which means oxygen vacancies move in these materials, and that is the primary failure mechanism for most electroceramics. And it also turns out to be what turns the ferroelectricity on and off in these materials. It's a little bit scary as a material system to work with because of that. Because if I don't get the oxygen vacancy concentration right and fixed in the material, they'll wander as I apply electric fields. And so among the things that we're working super hard on is to try and understand in real scale devices from global foundries exactly how you turn these materials on and off. The reality is they're always mixed phase. We always have some of the ferroelectric phase we care about and a parasitic phase that is not functionally ferroelectric. And that influences how well we can turn the channel on and off in a ferroelectric field effect transistor. This is a series of TCAD simulations that says as long as I've got at least 50% of the material which is ferroelectric, my memory window stays constant. So that's good. And here is another place where we can come back to energy. So remember, part of what drove this in the first place is we were trying to get to low temperature electronics. One way of lowering the low energy electronics, one way of lowering the energy barrier is just to get things stacked. Another way of lowering the energy barrier is to do learning fast in systems where you're actually trying to learn doing compute in memory. And it turns out that most people who do compute in memory try to set it up in an additive way, where I start with some device in one particular state, and if I want to modulate that state, I just basically provide a little pulse, and I try and make sure that I get exactly the same increment in change in polarization for every pulse. It makes programming easy, and it increases the energy burden associated with that learning by about 33% relative to a multiplicative learning. So another of our colleagues, Abhinav Sengupta, has demonstrated if you actually let the ferroelectric do what ferroelectrics want to do, which is to behave cooperatively, you can actually get a multiplicative learning process. And it drops the energy barrier associated with training relative to the conventional spiking timing dependent plasticity approach. So there's all sorts of things that we think will be really important if we can make this happen. And like you guys do this for a living, so I'm kind of preaching to the choir here. But anywhere I need to do anything data intensive, if I can learn fast, if I don't have to spend the time to get information from memory to compute, I can do things that are very complex in a much more energy-friendly fashion. So I am incredibly beholden to all of the colleagues on our team for everything you've seen here. Let me just tell you, the first publications on these new ferroelectrics came out last year. This is like fresh science. We're learning on the fly. It's been an enormous amount of fun. And with that, I'll make my final conclusions. Ferroelectricity is hiding lots of materials. So we can go find it. We can go choose materials that we want to turn ferroelectricity on and off. We think one way of doing this is by poising materials on the brink of a structural instability, making their susceptibilities big. The new Wurtzite structured ferroelectrics offer this amazing ability to deposit relevant materials, which are not just fab friendly, but like the fabs are like, I'm comfortable with this. This is fab comforting materials. At temperatures, they're like, they're not gonna be upset about this. 400 C down, you've got the back end of the line, you've got it to work with. We've had to develop some new understanding of these new materials. They're not the same as all conventional ferroelectrics. And there is an ongoing, incredible need to reduce the coercive fields so we don't engender failure modes associated with the fact that the fields are brutally high. So with that, I would like to thank you for your attention for this talk and for being very gracious and very friendly hosts over the last 3 days. Thank you.
Thank you very much, Susan, and for heroically going through when your voice is on the verge of disappearing. We're opening for questions. Let's see, I saw Frank.
Susan, you said it's very hard to verify the switching mechanism
Yes.
related to boron, for instance.
Yes.
I'm wondering whether that wouldn't be a nice system for a direct atomic resolution imaging experiment in one of these super in situ transmission electron microscopes.
So we're trying that experiment. Elizabeth Dickey from Carnegie Mellon is the one who's doing the work. The challenge is that these materials are granular, which means that the columns are tens nanometers in thickness. It's actually hard to thin it to a single column in thickness. And when you end up overlaying two columns, it's really hard to find the wall motion. So we're trying, we're not there yet.
So you always want the structural instability in your border. So Andrew's work shows that you go from anti-ferroelectric to ferroelectric.
Yes.
So right now your interest is using it as ferroelectric, but there is instability just there too. Is there any interest in looking at that instability between anti-ferroelectric and ferroelectric?
So that's a beautiful question, and Andrew speculates that that's going to be the way to drop the coercive fields in the material. Right now, the antiferroelectric phase has a fairly large energy difference relative to the cubic phase, and he speculates that if we could destabilize that antiferroelectric phase a little bit, make it a little less stable, it would be less energetically burdensome to switch it once it actually transforms to the ferroelectric phase. We'll see. So yes, beautiful question.
And I'll just ask questioners, speak up with your questions so we can be sure that it's becomes part of the audio from the recording. So,
So I had a couple of detailed questions. What is the rationale, or is there a simple way to understand why you can drive up the solubility limit by a factor of 10 when you go to a thin film?
We are growing under conditions that are nowhere near thermal equilibrium.
Okay.
And that's probably the first thing that we're doing, is we aren't getting, at 200 degrees C, these are strong bonds. We do not have enough thermal energy to take an atom that sticks here and move it a micron away to go find a comfortable position.
Okay.
I think that's what we're doing.
Okay.
It's just we're kinetically trapping it into the lowest, the easiest crystal structure.
So does that mean there might be a stability problem if it gets warm?
So we've certainly taken these devices and left them at 300 degrees C for long times without problems. I anticipate that if you took them to 600 or 700, where now the mobilities are starting to go way up, we would have problems, that it would start to solve some of the magnesium.
Would that be a realistic circumstance?
So think about how hot your processor is.
Yeah.
How many of you are comfortable carrying around a processor that runs at 600 degrees C? That would be no, that would be energetically costly. Probably 100 is as hot as it's going to get, at most 140.
There are points that get hot.
There are
and-
points that get hot, but probably not the 600 C
Yeah.
hot. Yeah, they want to keep everything, if you actually ever let things go above 400 C, you start migrating the dopants and the silicon transistors themselves, so you don't ever let it get past that point. If you need it to get hotter than that, you switch away from silicon.
Can I ask a related question?
Go ahead.
So I just was wondering, so you're using one sublattice for substitution, but you're using, in one case you're using anions, the other case cations. Is there ever a reason to try and use both? Or
The
is-
answer is probably yes. We haven't done it, but the answer is probably yes.
Just curious.
And I have a question. Early in your talk, you showed some schematic diagrams of these three-dimensional architectures, and I didn't see the details quickly enough. But so would there have to be metallic electrodes
So-
interpenetrating?
So if you look at a modern integrated circuit, you got one silicon chip, probably have 14 levels of metallization on top of it now. That does the interconnects in the chip. So they're all separated from by really low dielectric constant silicon oxygen, silicon oxide porous materials. And yes, they run all that metallization above the interlevel dielectric. We're probably going to be talking about putting the memory on top of that piece so that you've completed all the interconnects already, which means now if I'm going to make a transistor, I have to deposit my ferroelectric and all the ancillary electronics, including this new semiconductor, which probably won't get to be silicon front end, above that. And so our front order material that seems to be working very well is zinc oxide. So zinc oxide itself is a pretty good ferroelectric, or pretty good semiconductor, excuse me.
Okay, I don't see any other hands up, and so I think I will turn the floor over to our department chairman, Professor Frank Ernst.
Thank you, Mark. I would like to give it one more chance for a question from the students. Anybody?
There we go.
Great.
You mentioned about parasitic fields while you were explaining about switching on and off mechanism. Could you explain a little more about that?
So I heard part of the question about turning the switching on and off. Okay, so imagine that we start the material all with the polarization in the down direction. Almost always in material science, if you want to make any change, it's easiest to do that if you have some nuclei pre-existing. Very often, nucleation provides a big barrier. And so the polarization reversal process is typically a nucleation and growth process. And I start with no nuclei. So I start with everything in one orientation. The first couple polarization attempts to run a polarization reversal cycle, I think what we do is make the nuclei. And then once we have some nuclei, so most of it's still in this orientation, but we now have a couple of nuclei with the orientation in the up direction. Now if I have that nuclei, then during the field cycle, that nuclei can grow. And as it grows, it covers a larger volume of material. The more nuclei I have, the easier it will be to sweep the entire volume of the ferroelectric into the opposite polarization state. Does that help?
Yeah,
Okay.
thank you.
Great.
Yes.
You showed how the wake up make the ferroelectric switching difference larger, right? So is there any aging effect, like if there any reversal, right? if you like put it for a long time, does it stay steady?
At room temperature, we have not found it yet. So we've woken up capacitors and gone back and looked at them months later, and they're still awake. We are now accumulating the data that says, can we put them back to sleep if we store them hot? And I don't have the answer for that yet. You know, so like, can I pull the nuclei out? It's a barrier. Like anything else that has a perimeter, there's a surface energy associated with that. So I might want to get rid of it. And we just don't know how fast that will happen. So that's a beautiful question. I don't have a proper answer yet.
Yes, Laura.
You talked about problems at the interface between the electrode and the dielectric. Have you looked into like passivation layers or like a molecular modifier to fix that?
We use a lot of what we call helper dielectrics. So put down a little alumina, tidy things up, swallow the fact that it's not ferroelectric, and so I'm going to get a capacitor in series. But the permittivity is low enough that's not completely devastating. We do that routinely. What we'd like to do to keep the coercive fields as low as possible is minimize that. So we're doing lots and lots of experiments now on things like thermally stimulated depolarization current, charge-based deep level transient spectroscopy to try and go find what the defects are in that level. And hopefully we can figure out, once we know what they are, about how better to passivate them. So your question is a beautiful one. We don't have the answer yet.
I don't know how to check to see whether there are any questions in the chat, so
On top.
We could talk about 3 items. Oops, no, it's gone.
I think it was 3 at the beginning of the.
there.
All right.
Okay.
No other ones.
No questions. Okay. All right.
Okay, nevertheless, I think we can safely conclude, Susan, that you have passed. And you have passed the 3rd time, even with a question from an undergraduate student.
Excellent.
Yeah.
So that's an extra pass. Okay, so what remains is that on behalf of the entire department, we'd like to thank you so much for this firework presentation on ferroelectrics in microelectronics, which in my personal view even topped the first presentations that you gave. And I'd like to thank you so much for coming out here for these 3 days, being our guest. And you've been such a pleasant guest. You did everything we wanted you to do. Particularly, you engaged with our students intensely, and I think you fulfilled every criterion of an excellent Van Horn lecturer. We hope that you get better soon and your voice will return and you can recover from this particular stress of being a Van Horn lecturer and you get home safely. You should know that you made a lot of friends here and you're welcome to return here anytime and every time, and we will be happy to welcome you, and we count you as a member of our community here. Thank you so much for these excellent 3 days.